So coming to first of all the prerequisites of the workshop, we need AXA protocol basics that I'm keeping in the chat box. So you can refer this particular uh, playlist which is present on our channel. Let me share my screen also. So if you know about the AXA protocol, then only you will come, then only you will understand how and what we are discussing and all. Okay, or else it will be like it will be you will not be able to understand that particular thing. Okay, so just you can refer to what are the channels, and we are not going to implement this burst and all. Okay, so we are just going to implement a light AXA light. So only up to handshaking is enough. That's it. Okay. So this you can refer, and if you are a person who don't know anything about AXA protocol, I recommend you to watch those particular sessions. Right now, so and apart from this, the FPGA I have shown you, right? In the group, I have texted about the FPGA related thing. So try to have that particular FPGA related thing also, so that you can able to relate what I'm discussing, right? Okay. Now, so let us try to first of all once brush up the AXA related terminologies, so that we can able to start our session, right? So, can anyone tell me like how many channels are there in our AXA protocol, and what are those? What are the channels which we are going to have, and what are those channels we are going to have? Anyone wants to answer this? Exactly. So they are basically five channels we are going to have. So first one is we are going to have, yeah, five channels. So what are those? Anyone wants to answer? What are those particular channels? Write address, write data, read address, and read response channel. Exactly. So we have basically write address channel, and write data channel we are going to have, and we are going to have read address channel, and read data channel we are going to have for read operations, and also the last channel we have over here is response channel. Exactly. So these are the five independent channels which we have in our AXA protocol which we are going to use, and you can have this channels parallelly which you are going to have, right? Now, so before going to start with this particular thing, first of all let us see some prerequisites which are needed over here. Yeah. So what we are going to do is we are going to implement a FIFO. Okay. So generally we are going to implement a FIFO, but we need to establish the communication of our FIFO with our processor. So here I am going to use a processor which is known as Zinc processor. Okay. So this will be my Zinc processor. So this will be my entire FPGA chip, where this particular Zinc chip is divided into two parts. One is programmable system PS, and another is programmable logic PL. Okay. So whatever the code you're going to write down using your Verilog or using your VHDL, right? Using your HDL languages which you're going to write, that will be basically fabricated or implemented in your PL side. Okay. So in our workshop, we are going to develop a FIFO. So the FIFO code will be fabricated inside this PL. Okay. This is nothing but your processor. On the left hand side, which I'm showing you, right? This is nothing but my processor, and this is nothing but my FPGA, which I'm going to have, or programmable logic, which I'm going to have. The fabric, which I'm going to have. Now, this FIFO, if I want to communicate, if I want to establish the communication with my processor, with my FIFO, okay. Before that, what are the signals which we have for our FIFO? Can anyone tell me? If I'm going to have a simple basic FIFO, what are all the signals I do have here? I have clock. Next, reset signal I do have, and next, write enable. Next, read enable. Next, we do have like data in, right? And we have data out, and we have full and empty. So these are the signals which we have, which are associated with our FIFO. Okay. Yeah. So these are the signals which are associated with our FIFO. If you're a person who don't know about FIFO also, please once revisit this particular concept of FIFO, so that it will be clear like what I'm discussing over here, right? So these are the signals which are related to my FIFO. Okay. Now this FIFO, if you want to establish the communication with your processor, you cannot directly establish the connection, right? So this FIFO should be wrapped into another module. We need to have another module. This particular module is going to have AXI interface connected. So this particular module is going to have AXI interface connected with it. So this is nothing but my AXI underscore top. Let's say it has AXI underscore top. Inside this top module, I'm going to instantiate whatever the design I'm going to have. And this top module is going to have AXI signals associated with it. Okay. Now, using this particular AXI interface signals, which I'm going to have in my top module, I'm going to establish the connection with my processor. So in between, I'm going to have something known as interconnect. So this is nothing but AXI interconnect I'm going to use. And this particular FIFO is basically wrapped inside another module, which is known as AXI top. And this top module is going to have my AXI interface. Okay. So basically, this is what we are going to establish. Is it clear, guys? What is that we are going to do in our workshop? Is it clear? Yes. So in the playlist, if you have observed, we have just learned what do you mean by AXI and how we are going to use this AXI signals and all. Now, in this workshop, we are basically trying to establish the application of that particular learnings. That's it. Okay. Now, so let us see some of the system specifications and documents over here. So here the system architecture, AXI Lite FIFO slave bridges the processing system and programmable logic on Xilinx Zinc SoCs, as I've shown you, right? And basically, in your Zinc SoCs, you are going to have this processor, which is ARM Cortex A9, and it is going to communicate with a PL. PL is nothing but PL is nothing but your programmable logic via the memory mapped EXLR transactions. Okay. So identical to a normal memory write or read software perspective. So you're going to have a processing system, which is basically of ARM Cortex, and it is going to run C codes, whatever the application you're going to write, that will be in your C language. And you're going to use one software which is known as Vitis. Let me show you whether I have that. Yeah, this is the software which you're going to use, which is known as Vitis. In the software, you're going to write down the C application codes and you're going to program your PS side, processing system side. Okay. And if you want to program your PL, you're going to use this software which is known as Vivado. Okay. So for programming your FPGA fabric, you're going to use Vivado, and for programming your PS, you're going to use Vitis. Okay. And AXI interconnect, this AXI interconnect is basically present in your zinc fabric. So it is basically used to establish the connection between our processing system and our programmable logic. Okay, and AXI FIFO slave is what is that we are going to write down. That is nothing but my top model, which I'm going to implement it in my programmable logic, which is nothing but my FPGA. And another is this is the actual design, which is basically present inside my top model. I've shown you this block diagram, right? Where is this block diagram? Yeah, this one. So this two we are going to implement. Okay. So why we are going to use top model for establishing the connection. Okay. Now, so this is what we are going to have. And this was about your AXA Lite channel overview. I will share this particular document. You can refer to this AXA related signals that we are not going to discuss now. Yes. So we are going to have. So why does AXA Lite have separate address and write channel signals? This and all is related to the AXA thing. You can refer to this particular document or you can refer to the playlist also. Okay. Now, so let me open the Vivado now and let me open the block diagram. Okay. For you, let me delete everything and let me show you from the starting. So this is nothing but your Vivado block design or IP integrator window, which you're going to use. Now here, what I'm going to do is I'm going to click on this particular plus button and I'm going to add something known as zinc. Okay. Now this IP, I am adding it to my block diagram. Now, why I am going to add this IP? Because if you carefully observe in the block diagram which we have discussed here, this is nothing but my processor. this processor needs to be configured. Okay, so first of all, before going to establish the connection between your processor and your programmable logic, you need to configure your processor. You need to configure your processor. What do I mean by configuring your processor means? So your processor should generate clock. Your processor should detect your PL. Okay, this and all process will happen. Okay, so for happening this particular process or configuring your processor, you need to add that particular processing system inside your block diagram so that it will be configured. And after adding it, you are going to click run block automation so that Vivado is going to take care of this block automation and it's going to queue. Okay. And if you carefully observe, let me double tap on this. So let me wait. Yeah, this is your block diagram of your processor which you are going to have. And if I can zoom, let me show you. Yes. So you can see over here we have 32-bit AXI master ports and 32-bit GP AXI slave ports. Okay. And you can see this is my programmable logic. Whatever the Verilog code or VHDL code will be present, that will be present inside this fabric. And if a processor wants to communicate with this fabric using this ports, it is going to communicate. Okay. If you want to configure these ports, if you want to activate these ports, you need to first of all add it in your block diagram, block design. Okay, and you can see the processor is generating the clock. Okay, your PL, if your PL wants a clock, then your processor is only going to give. There is no direct connection from external clock source to your PL. Okay, can anyone before that tell me how you are going to generate a clock? Anyone knows how you are going to generate a clock physically? Exactly. You're going to use a crystal oscillator or you're going to use a PLL. Those type of circuits will be present physically, and from that you're going to generate a clock. Okay. So if you're going to generate a clock, so that particular clock circuit will be present inside your development kit only. So that particular circuit will be present inside your development kit, and this particular whatever the crystal oscillator which is present. So there is no direct connection from this oscillator to your FPGA in our Zinc architecture. So what are we going to do? This particular clock connection will be present to your processor. Now processor, it is going to give it to, or it is going to forward it to our PL. Okay, so you can see over here, we are going to have this particular clock connections. The processor is going to get the reference clock and it is going to generate the clock and it is going to give it to our PL. Okay, so for configuring this and all, we need to have this IP present inside our IP present which inside our block design. Okay, so yeah, and this and all we will discuss later, like what is this and all, and if you double tap on this, it will open. Okay, so this particular thing should be present so that you can configure your whatever the processor you are going to have. Otherwise you will not be able to write down your C level code in the whitest, as I've showed you previously. Now here the code I have already written for my AXI based FIFO. So this is what I have designed. AXI, in the AXI interface I'm going to have FIFO and all. I will show you one more time. I will show you in detail like what I've done over here. Just I wanted to show you how the things work from the top level view. So basically what I've designed is this particular design I have already done. So in the AXA top, I have instantiated my FIFO and every timing related thing, simulations, everything is done. So I just need to add it over here. So how to add it over here? Just right click on it and there is one option which is known as add module. So you need to add this AXI FIFO slip. Okay, let us try to add FIFO, not AXI FIFO. Let us add simple FIFO design. So this is what the FIFO design I'm going to have. You can see, right? So this is a FIFO design I'm going to have, which is going to have clock, reset, write enable, read enable, D in, D out, empty. And let me run connection automation and let me press OK. You can see only the clock and reset pins have been connected, but your write enable, read enable, D in, D out, full, empty are not connected with your processor anyways, because your processor, if you want to communicate with your whatever the RTL code, you need to have EXA interface which is present. If you want to make this write enable, read enable, D in, D out, a full empty, you can give it to external sources, but it's not going to work like that. Okay. So let me remove that. Is it clear, guys, up to here? What I'm speaking about, is it clear? Okay, I will explain one more time how I am going to add zinc chip. AXI FIFO slave. Yeah, both are same. And any other doubts? Up to here, please let me know. Okay, that's great. Let me delete it. So how to add this zinc is just right click on it and click on add IP and type zinc so that you will get your IP. Okay. Now, so what I'm going to do is again I'm going to click on add module, and here I'm going to add this AXI FIFO slave or whatever the top model which we have seen, right? This top model I'm going to add it. Okay, I've already designed it. No worries, I will show you the design also how to do it. Okay, yeah, you can see over here. Vivado automatically detected that it's an AXI interface and it has created an interface for it. Let me zoom in for you. So Vivado automatically detected that we have created a AX interface, and it has created a port like structure. Okay. So if I click on this, I will get expanded view of what are the ports which I'm going to have. So this is a good feature in Vivado that it is going to automatically detect a particular interface which is present, and it is going to create it as interface. Now let's say suppose if I'm going to add my FIFO, let me show you. See, so this is also the type of signals, but it's not related to any standard interface signals, right? So that's why it haven't created any port like this. Okay, so that is the difference between the interface and normal signals. And here, I don't need to worry about any type of connections. Just I can click on run connection automation so that everything will be added. So what is going to be added? Let's see. So I'm going to have a bridge. So which is nothing but AXA Smart Interconnect. I cannot configure it, and I'm going to have this master interface. Let me click OK. So from master interface, let me show you from where this connection is going to happen. So you can see, right, M underscore AX underscore GPA, general purpose, this particular thing. Let me elaborate this. So this is master related AXS signals which are present with your processor. So you can see AR valid, AW valid, B ready. These are all are outputs, and these are all master interface AXI signals. Okay. So this particular M underscore AXI GPIO will be connected with our slave interface. Okay. So if I'm going to click on run connection automation and click on OK, that's it. So see, let me rearrange this. So for rearranging this, I can just click on regenerate layout so that the layout will be reset. You can see automatically an interconnect has been given. So this interconnect, what it is going to do is it is going to connect the master's interface to the slave interface, and it is going to convert it into again master, and this interface is connected to this particular thing. Okay. So see, our AXI FIFO is connected to our master via the interconnect. Okay. I can also expand this. These are the signals which are present. Okay. Yes. So this is what we are going to do. Is it clear, guys? No, EDA Playground don't have this feature. We need Vivara for this. Is this a crossbar with multiple masters and slave ports? Yes. We can also have multiple masters and multiple slaves ports. We can add it. We can configure it. Yes. Any other doubts or any other queries in this? Okay. Yes. Okay. Now, after doing this, you can just click on Control S, which saves your design, and you need to validate it. So, how to validate? You can click on this particular button. Your design will be validated, and it will give you like if there is any error, or if any pin is missing, or if there is any mismatch in the width of the ports and all. That analysis will be done by the Vivado tool, and it is going to give. If there is no error, you are going to get validation successful. Okay. That's it. So this is how you're going to generate your design. And this particular design, you're going to, for this particular design, you need to, what to do is, you need to click on this design, block design, and right click on it. And there is an option which is known as create HDL wrapper. Okay. and click OK. Let Vivado manage everything. So this wrapper is nothing but it's a file which is going to wrap all these particular files into one particular file, and it will be treated as a top module. Yes, I can see over here it is being generated. And yeah, so this is nothing but design wrapper. So it is basically a wrapper of all the particular files which we are going to have. And I need to make sure that it is set as top. Set as top. We haven't started with coding, guys, yet. I'm basically showing you like the top level overview of how the things are going to work, and later we are going to see the coding. So that if we have discussed the top level view, then it will be like you will also be having some enthusiasm for running the code. Okay, yeah, this is the design wrapper which I have set as at top. Then after that, you need to generate the bitstream. Okay, so you need to generate the bitstream. So if you are going to generate the bitstream, what is going to happen is a hardware file will be created and a bit file will be created. Okay. So if you're going to generate a bit stream, the design will be synthesized and the implementation will be done and everything will be done. And a hardware file will be created and a bit file will be created. Okay. On this particular hardware file, you're going to develop a application. This will be your C level application which you're going to develop in Vitis. If in your Vitis, if you're going to develop your C level code, you need a hardware file. Okay. So that particular hardware file, this is your hardware file that you have generated. And on this particular hardware file, you're going to develop a C level file in Vitis. Okay. So that and all we are not going to in great detail, but I will show you some commands like what is the software people or embedded people going to do in the C level code. Let me show you that particular thing. Yeah. So after creating the bit file and generating the bit file and going to the Vitis environment, this is what you're going to do. You're going to write this code where you're going to give some base address, range, and high address. Okay. Now, what is this base address, range, and high address? Let us try to understand. Now, if your processor wants to communicate with your FPGA or the programmable logic, your processor don't know what is which is present inside your programmable logic, whether it can be FIFO or whether it can be any module which is present. Your processor don't know anything. Okay, your processor just know two things. One is offset address and another is starting address and the address boundary. Your processor know that's it. Okay, so how to and what is this particular address? Let me show you in the Vivado tool itself. Let me show you. So there is one option which is known as address map. So here we need to first of all generate an address map. Let me create on generate the address map. Yeah, this is what the address map the Vivado has been created. So your processor can only see these addresses. So the starting address is this particular thing, and the last higher address is this. Okay. So your processor is going to look at these addresses, and if you are going to if you are going to issue these addresses only, then only your processor is going to communicate with this device what you're going to have. If you're going to give the address which is not present in this range, you cannot establish the connection between this processor and the FIFO which we are going to have. Okay. You need to first of all generate this address in the Vivado itself, and then you need to proceed with the bit stream generation. Is it clear, guys? Hope the things are not complicated. Okay, only one response. What about others? Okay, okay. So if you have learned about computer organization, I think things will be a little bit familiar with what I'm discussing about. Okay, no issue in that. Now, so here you can see over here. So if I'm going to have the base address and the range of the address and the high address I'm going to have, this is the just example addresses which I've given over here. And this is one of the command which I'm going to use xil underscore out underscore 8, which is for 8 bit. And I'm going to give the base address. Okay. FIFO underscore base underscore address. So FIFO underscore base underscore address is this particular thing. Okay. If you are going to give this address only, you are going to you're going to perform the operation. Okay. And you're going to give the data which you want to write. Okay. And if you want to read, you're going to use another command which is known as xil underscore in8, which is basically for reading. And you're going to give the base address, and then only you're going to perform the read operation. Okay. You might have a doubt over here. So FIFO, basically we are not going to give the write address and read address. In the block diagram also you have discussed that FIFO is not going to have any signal as write address and read address. Yes, FIFO is not going to have any external signals like as write address and read address. But if your processor wants to establish the connection with this IP, you need to provide that particular address. Then only it is going to establish the address. Okay. Yeah. Is it clear? The address part, is it clear, guys? Okay. That's great. Now, so this is what. So we are if we are going to have more number of modules like DDR or RAM or some AXI FIFO and all, for each and every component we are going to have some set of addresses like this. Okay. Yeah. So this and all the signals which are related to that particular thing. Yes. So if we're going to use a particular command, this and all the signals and the code explanation all and all, I will share this entire document with you so that you can have a look into it. First, after developing our code, we are going to have this particular document. I will share it with you. Okay. Now, if I'm going to have this, if I'm going to call this particular, where is this? Excel underscore. Yeah. Where is this? Yeah. If I'm going to call this particular uh, function xl underscore out 8, internally it is going to assert whatever the signals we have like aw valid and aw ready and w valid w ready. This and all signals will be internally taken care, and they will be asserted accordingly. And the sampling of the signals which we are going to get from the slave like w ready and aw ready, those and all the signals will be sampled by this processor internally. Now, if you're going to use this command and if you're not going to, if the processor is not going to get the signals on the time, then the processor will stall. Okay, it is not going to work at all. Okay, so this type of signal, this type of situations you might enter when you're going to work with the real-time hardware. The timing is very, very important. So it might not sound very familiar like what I'm speaking about if you're not working with an hardware. Okay, it's not an issue and it's not a scope of this workshop, right? So that is what we are going to establish, and this is why we are going to have this AXI based FIFO. That is the reason we are going to design this AXI based FIFO. Okay, is it clear? So why we are learning this AXI based FIFO? Is it clear? The motive, is it clear? So this is the reason we are going to learn, and this is the reason we are going to implement. Okay. Yes. So from the next session, we are going to start with the development of the FIFO design, and we are going to develop a wrapper. And first, we are going to develop the test bench, and we are going to check in the simulation. Yes, address is not given to the FIFO now, as I've said, right? So if the processor wants to detect a particular device, it needs to give in a base address. It's not, we are not going to give it to the FIFO. We are giving to the processor.